Welcome back to Physics 141 Online. What I'd like to do now is just spend a couple of minutes reviewing very basic calculus ideas. If you haven't covered this in your math course yet, you'll be doing it very soon. And I'm only going to expect you to understand a very simple rule for finding the slope or the derivative of simple functions of time. So the goal here, since we know that the slope of the position versus time graph is the velocity, and we know that the slope of the velocity versus time graph is the acceleration, we want to be able to start with a position versus time function, and from it calculate velocity versus time, and then use that to calculate acceleration. And perhaps that acceleration is constant, perhaps it has a time dependence. So again, just to summarize, remember what we talked about before when we defined instantaneous velocity. The instantaneous velocity, written dx dt, is the slope of the position versus time graph, and likewise the instantaneous acceleration, or dv dt, is the slope of the velocity versus time graph. And so all I really want to do is show you a couple of examples of rules for finding the slopes of simple functions. And it doesn't matter whether it's a function that represents position versus time or velocity versus time, the way you find the slope is the same. And that slope, once again, in mathematical language, is called a derivative. So when you have a function, x of t, let's say, that has a very simple power type dependence on time, all of the parts of the position function are terms that have time to a certain power. Okay, then calculating the slope is really easy. So here, using symbols here, imagine that x of t, the position versus time, is given by a constant b times the time variable to the nth power. And if b and n are constants, then the velocity, which is written d, and in parentheses we put the expression for x, bt to the n dt, all right, that's how we pronounce this, btn dt, is equal to something that looks like this. Now where does that come from? What happens is the power n comes down in front as a multiplier, right? So it's n times b, and in the process of finding the slope, the exponent for the time variable gets decreased by 1. So if x is bt to the n, then v is nb t to the n minus 1. And just to make sure that that's crystal clear, here's an example with numbers. Imagine that position versus time is given by 6t squared. Then the velocity function, the 2 comes down in front as a multiplier, so 2 times the 6 that was already there, and then it's t to the 2 minus 1 power, right? 2 goes down to 1. So 2 times 6 is 12. T to the 1 is just the same as t, so the velocity would be 12t. Right? And if the function that's given had been the velocity function, we would find the acceleration function in the same way, because acceleration is the slope of the velocity function. Now just to mention these, because they will appear later on in the course at some point, we might have occasion to want to know the slopes or the derivatives of other simple functions like trigonometric functions and exponential functions. And we won't do anything with these in Chapter 1, but I just list them here for your own benefit. If x of t is some constant times a sine function, where there's a constant multiplied by the time variable inside the argument of the sine, then the velocity, what happens is we take the derivative of what's inside the parentheses first, and then the sine, when we take the derivative of the sine function, it becomes a cosine function. So we start with a sine of bt. Well, the b comes out in front as a multiplier. The a is already there, and sine becomes cosine. The argument stays the same. All right, so that's the rule. I can show you where it comes from sometime. You'll undoubtedly learn how to derive something like this to see where it comes from in your math course, but that's the answer. Likewise, cosine is very similar to sine, except that the derivative involving a cosine function brings back a minus sine function. So otherwise we end up with the same basic outcome. The b that was inside here comes out as a multiplier, but there's a minus sign when we take the derivative of cosine to get minus sign. And lastly, just for completeness, exponential functions are often encountered in physics problems. So if the position versus time function was a constant a times e, the exponential, to the bt power, then the velocity would be that same derivative, and the same thing happens. The b that's multiplying the time comes down as a multiplier, so we get b times a, but the exponential function has the really curious property that the derivative of it, or the slope of it, is proportional to the function itself. Right? So originally we saw up here how the slope of the sine function is related to the cosine function. The slope of the cosine function is related to minus the sine function. Here the slope of the exponential function is related to the exponential function. So it has this interesting property. Okay, so what I really want to focus on right now is a problem where you will make use of the simple rule for finding the slope or the derivative of these polynomial type functions in order to do interesting kinematic calculations. So here's an example, again, from an exercise in the textbook, Wolfson exercise 2.51. And here what he gives you is, we don't worry about where this information comes from, but let's just assume that a moving object has a position given by x equals bt cubed, where x is in meters, t is in seconds, and the constant b has to have units of meters per second cubed, and I'll use a number 2 for that. Your number that you get when you do the online homework will probably vary. It may even have a slightly different function. But how I work this problem out will apply to the one that you have to do as well. And there are 4 questions that are asked. What I'd like to do is actually focus on A and then C, finding the instantaneous velocity at a certain time, and then finding the average velocity over the first 2.9 seconds. All right, and once you see how to do A and C, you'll be able to see how to do B and D as well. So here's the problem written out on my sketchpad. We know the position versus time function, and we're trying to find out information about, in part A, instantaneous velocity, part B, instantaneous acceleration, and then part C and D, the average values. Realize, first of all, that when we write down instantaneous, it means that we want to know what the value is at a particular instant, at one particular time, and that's 2.9 seconds. When we talk about an average, inherently, because of the way the average is defined, we're talking about an interval of time, from an initial time to a final time. And this says in the first 2.9 seconds, and so what that really means is from time equals 0 all the way to 2.9 seconds. That's the range of times over which we're going to calculate the average velocity. Okay, so instantaneous means happens at an instant. So the first thing we want to do here in the I, of course, is we know this is a 1D motion problem, but it's a problem where we are going to not use our kinematic equations for constant acceleration, but we're going to actually use use x of t to find v of t and ultimately the acceleration as a function of time. All right? So we need to use our simple calculus equations for finding slopes. V is the slope of the x versus t graph. A is the slope of the v versus t graph. So for D, we're going to use our simple calculus formulas, the ones that you just saw a moment ago, because the kind of function we're given is a simple power function. All right, so we're going to do parts A and C here, and then I'll let you do B and D on your own because I think it will become clear how to do that. But first, before I even start to solve part A, let's just calculate V and A, starting with x. All right, so I'll just rewrite it. X is equal to bt cubed, and now we know that V, which we write as dx over dt, and we call that the derivative of x with respect to t. We have the power that comes down in front, so we get the 3 multiplying the b that's already there, and then the t now ends up with a power that's 1 less, so it's t squared. And if that's not clear, go back a couple of slides to the PowerPoint and see where that comes from. Alright, so that's v of t, and now I can do a as well, because now I have the expression for v. A is the slope of velocity versus time, or the derivative of velocity with respect to time, and we do it the same way. The power of t comes down in front as a multiplier. There was a 3b that was already there, and so that stays, and the time gets reduced by one term, by 1 in the power, so it's t to the 2 minus 1, or just t to the 1, so we end up with 6bt. Right, so these are the two expressions that we need in order to answer A through D. So now part A, well, instantaneous velocity at the end of 2.9 seconds. That's easy, right? So just evaluate v, right, for t equals 2.9 seconds. That's simple. So we go v, and I'll just make it clear that we're doing it at a particular time. So it's v at 2.9 seconds. It's equal to 3 times b, so we've got 3. B in my problem is 2.0 meters per second cubed, and once again I'm putting the units in. I'm going to be careful about this. T is 2.9 seconds, and then we square it. Okay, so the numbers are easy enough to work out here. The number that you get when you evaluate this is 50, and it's 50.4 actually, but I'm just going to call it 50 because there's only 2 significant digits in these numbers. So 50, and then what about the units? We have meters per second cubed times second squareds, so we have meters per second. And the only thing we can do as far as assessing this is we can look at the units. And the units are okay, because we're trying to calculate a velocity, and we got a velocity in meters per second. That makes sense. Whether 50 is reasonable is kind of hard to say, because we don't really know too much about this object. But the units do make sense. So that's part A. That's really pretty simple. In part B, you will do much the same thing using the acceleration expression. Right? You find the instantaneous acceleration at 2.9 seconds. So I'm going to move on to part C, because it's a different kind of problem altogether. It asks for an average. So average velocity. Well, go back in your notes, or your book if you've got it, and go back to the definition of the average velocity v bar. We know that it was written as delta x over delta t, the change in x divided by the change in time. So that always means that there's a final x value minus an initial x value, and a final time value minus an initial time value. Okay? So what do I do with this? Well, x final means the x at the end of this 2.9 seconds. Right? So here's the expression for x. Well, I'm just going to write down b, and t, I'll call it t final. Ultimately, I will plug in a value for it, because it's 2.9 seconds, but let me just call xf b times tf cubed, using this expression right here that was given for x. That's x final. X initial is b times t initial cubed. And the denominator is very simple. It's just t final minus t initial. Okay, now having written things out symbolically, I'm ready to plug in the values that I know. T final is going to be 2.9, because we want to find the average velocity in the first 2.9 seconds, which goes from 0 to 2.9. Right? But T initial is 0, because that's the beginning of this range of time. So T initial is equal to 0, which knocks out the second term in both the numerator and the denominator. So we end up with b t final cubed over t final, which is just b t final squared. And before even solving this with numerical values, I'll just emphasize the reason we do this symbolically is we save ourselves a lot of calculation. If we had rushed to plug in numbers in the original expression, then we would have several different things to plug in for and calculate. What we have here is simply one final expression. So this average velocity is simply b, which is, in my problem, 2.0 meters per second cubed, times t final, which is 2.9 seconds, and that needs to be squared. So the numerical value for this is right around 17. To two significant digits, it is 17. It's meters per second, right, because it's meters per second cubed times second squared. And once again, the units make sense. The units are okay here, which is about as far as I can go in the assessment step. Okay, but if you understand how to do average values and you understand how to do instantaneous values, then any kind of problem like this will be easy for you to do. So you'll have to do this problem yourself with the numerical values that are given in your problem, and you'll have to also work out parts B and D. But hopefully this is a good illustration of how to use very simple calculus formulas to treat problems involving one-dimensional motion.